Aribi, and this is my presentation on Lab 3 about black holes and orbits. So for a little bit of introduction, the purpose of this lab is to identify the effects of Newton's second law and relate it to momentum. So a little bit of a preview of this lab, we have the calculation of our black hole's mass right here, and then we have down here, which is from part 2 of this lab, the speed of the ship and the planet in the X and Y positions. Alright, so the system in this case is going to be the rocket, and then for part 2 we have the moon involved as well. The surroundings is going to be the black hole. Alright, so for part 1 of this lab, we did an orbit of a star around a black hole. So the fundamental principles of this lab were Newton's second law, which states the acceleration of an object is directly proportional to the net force acting on it, inversely proportional to its mass. And then we have our gravitational force, which is the gravitational force is the force between two masses separated by a distance, and it is a non-contact force influencing planets and everyday items. So the math for Newton's second law is right here. We have F net equals change in momentum over change in time. And then we can use this equation to calculate that F net equals F parallel plus F perp. And then we can say the gravitational force equals G times the two masses over R squared R hat. We can break this down, and then we can determine that the mass 2 is equal to this equation, which we will use later. All right, so now for the glow script model from part 1, we're going to take a look at this. So first, looking at the top parts, we have our gravitational constant, the mass of our star, and the delta T. Next, we have our initial and final velocities right here. We have our P equals mv here. We have our change in velocity and momentum calculations here. We have our dp over dt calculation right here, which this will be used to find the F net of our dp over dt, which is right here. Then we calculated the parallel change in P right here. And then we have the parallel F net right here. And then later down, we have the mass of the black hole. All right. And so then here is our code in action. And so then from this, we got an F net of 1.01307, 10 to the 29. We got our F net parallel as 3.74708 e to the 28. And then we have F net perp as 9.4304, 10 to the 28. And then we calculated our mass of the black hole from all of this. We took the averages of all of them, and we got 1.62591 times 10 to the 34. Alright, so for part 2 of this lab, we calculated the mass of a black hole to solve for initial velocity of a spaceship, ensuring it doesn't crash into the black hole. Okay, so taking a look at this code, we have our constants up here, which have our gravity and our masses, and then we also included the mass of the black hole. So then down here we have our initial planet speeds and velocities, and then these are our initial ship speeds and velocities, which was calculated due to trial and error. Alright, so this is a little bit more of our glow script model from part 2, and so here we have our F net on the planet, and then this is our F net on the ship. And then here are the results from part 2, and as you can see, none of these are colliding, and none of these are colliding with the black hole. So some possible errors could be some approximations. The simulation does not always represent reality. This could also be accuracy, which is trial and error used for the coding, and then our coding, of course, could have been more precise. So to answer the question of how is the net force and its parallel perpendicular components different from the rate of change of momentum in its components. So because F net equals dp over dt, mathematically they are the same. However, rate of change of momentum is much easier to calculate because the only thing you need to know is the system's change in velocity and momentum, whereas the net force you need to know all the forces acting on the system. For the what if question of what initial velocity does the spaceship need to orbit around the black hole, We calculated this through trial and error, and it was determined for the x speed to be negative 685, and then this y speed to be 668.3. And then here's the final picture of that. All right, thank you.